All right, well, good morning, grade nines. And funny story, I was recording for the last, I thought I was recording for the last 10 minutes. I guess I was just talking to myself. So I'm going to start over and listen, today we're almost done. We're almost done. This is really our last lesson and it's not very long. So I think you'll find it pretty straightforward. Um, all right, we've been talking about on and off talking a little bit about music for a little while now. We've been talking about, for example, how resonance works in strings, and that's the foundation for stringed instruments. We've been talking about how resonance works in hollow tubes, and that's how it works for wind instruments, right? So even though we haven't, it's not a class on music or anything, still, okay, nevertheless, we have been talking um, about sound and a little bit about music on the way, okay? Well, now today we're going to talk more about how humans experience sound, and part of that is how they experience music. Now, you don't need to be a musician to understand this, so please don't complain to me, oh, sir, I'm not a musician, I don't get it. Okay, you don't need to be a musician to get this, okay? Like this is not a course in can you play an instrument or can you sing a tune, okay? It's not like that, okay? But you're going to be hearing some sounds today. So I pulled over, it's basically the same piano that we have at school in my classroom, but I brought this piano here. Now, I'm not going to blow you away with my playing skills. I never took piano lessons, but I know how to play chords. So like, like I can play happy birthday and birthday to you, that kind of thing. And I've learned a few things that's good for a party. I can play certain songs that I've learned when I was a kid. And the Charlie Brown theme. So I can play a few songs. And yeah, just for fun. My son is way better than I am, and I'm sure probably many of you are better than I am at playing that. But anyway, why did I bring the piano? Like I said, it's not a performance. You wouldn't be impressed that much by my piano playing. But it's still I can demonstrate some of these things so you can hear, okay, the sound, okay, and you understand when you're listening to the sound what consonance and what dissonance is. And I showed you that today, but I'll show you one more time here, and really you need to hear it. And well, let's go ahead and start, and let's start with this concept of consonance and dissonance. So consonance, as I said to you yesterday, I guess, now that you're listening to this on Friday, tones that sound happy when played together. Now, happy is a bit of a subjective term, okay? Like I could say, hey, watching Star Trek makes me happy, but not you, right? Maybe it doesn't make you happy. What's wrong with you if you don't like watching Star Trek? But, I get it. So we don't mean that kind of thing. It's really a feeling that you get when you're listening to certain sounds that are played together. It's a bit hard to describe with other words, this thing called consonance, okay? Um, so I know I played some for you earlier today, but I'll play it again. So hopefully you hear this piano well. So playing a note like, or this, so if I sing the note like a one-to-one note, like, those, me singing it, it might not sound very pleasing to your ear, me singing, okay, I get it. But if it's the same note, it's consonant when sounded together, okay? Now, an octave, so an octave like that, which is an octave, we'll talk about this a little later today, it means double the frequency. So like if this is 240 hertz or something, then 480 hertz would sound like this. And when you play those two notes together, they sound very good together. So you see, they sound good together, like in a pleasing way. So this pleasing sort of way that they sound together, and you have to have more than one note to have consonants, right? So you have to have at least two notes, and they sound good together. Now you can have many notes. I could play like another note. Okay, that's four notes I was playing there. They all sound very pleasing together. That's what we mean by consonants, okay? Now, dissonance is basically not consonants. So they sound like unpleasant, unhappy, sad, that kind of thing. So, pleasing, whatever the opposite of pleasing is. Now, the thing is that's also a subjective term. And sometimes don't confuse it with desirable and undesirable, because you don't want all music to sound happy. Sometimes we don't want that, and I know we talked about that too. So dissonant tones could sound something like this. Okay, like this note and this note played together. And I can play more dissonant notes. That sounds dissonant. Now, we might not agree how the music makes us feel, but you understand, right, what consonance and dissonance means when you hear it. You know it when you hear it. That's consonant. That's dissonance, okay? And you get it when you hear it. And so that's why these words unhappy or unpleasant and everything don't really describe the feeling exactly right, okay? Because we're using subjective terms to describe it. But that's it, okay? So when you hear, you know it when you hear consonants. We all recognize it, okay? Now, what causes consonance and dissonance? What is physically happening there with the frequencies that would give rise to a consonant sound or a dissonant sound? Well, it turns out that there's a really simple thing going on there. And I'm going to highlight the phrase for you. Okay, if the frequencies of the sounds being played can be reduced, and this is the key, to simple whole number ratios. Now, simple whole number ratios. Therefore, the sound will be consonant, okay? So if that's the case, the sound will be consonant. Now, what do we mean by simple whole number ratios? Let me give you an example, okay? Let's say one frequency that you're playing is 440 hertz, right? Well, if I play another note that's twice as that frequency at 880 hertz, you can put that in lowest terms. Like, you know, when you put a fraction in lowest terms. So in other words, if I were to write 440 divided by 880, put it in lowest terms, it boils down to 1/2. Okay, because just divide the top and bottom by 440 and you'll get 1/2, and that's in lowest terms, right? So we have to put it in lowest terms, and what we see is that 440 to 400 and 880 is the same as a ratio of 1 to 2. Well, that is a simple, 1 and 2 are simple whole number ratios. Now, what we mean by simple is ratios between the numbers 1 to 5, no higher than that. Okay, no higher than that, from 1 to 5 only, okay? And if we go outside of that range, you're going to find that it gets more and more dissonant as a result. Okay, so let me show you another example, and this time of dissonance. So let's say one of the frequencies you're playing is 256 hertz, and the other frequency you're playing is 270 hertz. Well, that's going to sound like this. Now, if you put that in lowest terms, the best you can do is boil it down to 128 to 135. That's not simple enough, okay? So this is quite simple, okay? But this is complex, okay? Now, I know I wrote the word complex already here. I'll write it again just so I'm doing something. Okay, so that is too complex. If that's the best you can do to put that in lowest terms, that's too complex. And that's why, to your ear, those complex combination of frequencies sounds, the more complex that ratio is, the more dissonant it gets. In other words, the larger those numbers get, when you put them in lowest terms, the more dissonant it's going to sound. Okay, so like tones up here can sound very dissonant. It's the same kind of thing, okay? Or I can change it. You know, like these are dissonant notes because they make very complex ratios that can't be boiled down to just small whole numbers between 1 and 5. Okay, so what we want is the numbers to reduce, and like putting in lowest terms your ratio of frequencies, you want them to reduce to numbers, whole numbers, and I'm going to highlight this with a rainbow, whole numbers from 1 to 5, okay, will be especially consonant. Okay, whole number ratios from 1 to 5. Now, what do I mean by that? Well, let me give you an example. Okay. Let's say we start, I play a note for you on the piano. Okay. And let's say that note corresponds to a frequency of 150 hertz. Okay. Now, what note would sound consonant with it? Well, the second harmonic, which would be 300 hertz. These boil down to, these two here, to 2, 1 to 2. Okay. So that's how we write ratios with the little colon in between. So when you put them in lowest terms, it's 1 to 2. Very simple, very consonant. And like I said, it would sound like that. Sounds very good together. Okay. Now, what if we have the third harmonic? Well, the third harmonic would be 150 times 3. Okay. And 150 times 3 is what, 450? So it's 450 hertz. Now that will sound good together too. So watch, if I play all three of those notes, okay, so this is 150, 300, 450, play them together, and even playing 300 and 450, see, those two boil down to 2 to 3 in lowest terms. 2 to 3 is pretty simple. So here you can reduce this to 2 to 3. That is simple too. Now let's add the fourth and fifth one. So if I go F4 is 600 hertz, okay, and then F5 would be 750, okay. Now, if you put all these in lowest terms, these two here make 3 to 4, and these two here make 4 to 5, okay. And any combination of these, like I could play the first one and the fifth one, and they boil down to 1 to 5 in lowest terms. The first one and the fifth one would sound like this. And that sounds pretty good. That sounds pretty pleasant. Okay, so that's consonant. Not as consonant as an octave. That's an octave. Okay. Octaves. Not quite as pleasant as 2 to 3, which sounds like this. Okay. Or 3 to 4, which sounds like this. That's 3 to 4. 4 to 5 sounds like this. Okay, so it's like, and that is together, okay? These are all any combination that you can play. You could play 1 and 5. 1 and 5, you know, like we said. You can play 2 and 5. 2 and 5. Okay, it almost sounds exactly the same, doesn't it? You can play 3 and 5. 3 and 5. Pretty good. Now, if I play 6, now you're starting to get a little out of whack. So here's 5. 6 would sound like this, okay? Actually, 6 would still sound pretty good, to be honest with you. It's still not quite out of the picture. So it's 1, 2, 3, 4, 5, 6. But then 7, there is where it starts getting a little bit dissonant, okay? So once you get to 7, 8, 9, and you're putting them in lowest terms, you're getting like 7 to 1, whatever. 7 to 1 sounds like this. And that has a little bit of dissonance in it, okay? So my point is, you're playing notes in a band or in an orchestra or whatever. If they work out to simple whole ratios, when you put those frequencies in lowest terms, you'll get a consonant sound, okay? Now, if they don't boil down to very simple whole ratios, like if it starts getting complex, like 1 to 7, 5 to 7, stuff like that, 5 to 7, 4 to 7, like that kind of thing, 3 to 7, you're going to start hearing some dissonance there, okay? Now, the more you get out of there, 7, like 8 would be not too bad, but 9 being here, so it's like that starting to sound quite dissonant, okay? 8 and 9 together, sounding dissonant. So the deal is, dissonance is when it doesn't boil down to something simple. And the simpler they can be, 1 to 1 being the simplest, 1 to 2 being the next simplest. You get the idea? Okay. And then 1 to 3, 1 to 4, 1 to 5, and so on. And then 2 to 3, 2 to 4, 2 to 5. See, like even between themselves, they can be more and more consonant if the simpler you can make that ratio. Okay. So the simpler, the better. Okay. The simpler, the better. Now for dissonance, the more complex, the more dissonant the sound will be. Okay. So if it's like 1, 2, like, you know, like play something really low and then some note that's not quite there, and that will sound very dissonant. Okay. And dissonance is the more complex that ratio boils, like the numbers they boil down to. If it turns out to be a complicated ratio, like outside of the numbers 1 to 6, forget it. Okay, I know I wrote 1 to 5, but 1 to 5 is fine. Okay, so what it is, that's consonance and dissonance, okay? So it has to do with the ratio of the frequencies. Okay, when you put them in lowest terms, if they boil down to numbers between 1 and 5 in lowest terms, they're consonant. Okay. Now it just turns out that a very happy sounding chord is something called a major chord. Now a major chord is constructed by taking the first 5 harmonics, which I just listed them for you here for, you know, for say a particular example. The first 5 harmonics will sound highly consonant when played together because they're just the notes from 1 through 5 in lowest terms, right? So they should sound consonant, okay? And they do. So this is an example. I'll play a different chord for you. This is an example. That's an example. It's a chord called F major. So it starts with an F, but then you play the 3rd, 4th, and 5th harmonics, and you get a nice, you know, very pleasing sound. That is F major, C major, F major, B major. Okay, B flat major actually. But you see, these are the chords that we use when we want a pleasing sound, okay? Like a pleasing, happy kind of sound. Lots of popular music, if it's meant to be upbeat and kind of happy sounding, they use this progression of chords, right? Like it basically from here, you know, like that. One, the B flat major, those 3 major chords. It sounds happy all the time, you know? So, you know, there's a Mexican song, or no, I shouldn't say that. There's a Latin American song called La Bamba, you know. Right? It's happy all the time. It's meant to be upbeat and happy. Okay, and that's how it is. Some songs, not so much. Happy birthday. We want the guy to feel happy or the girl to feel happy at her birthday. You know, happy birthday to you. Happy birthday to you. Okay, now you can add some dissonance. Happy birthday to you. And then here, happy. There's some dissonance there. Happy. Still sounds good. You're adding the 7th harmonic. Happy birthday to you. As long as we work it out, okay? And then happy birthday, happy birthday. That's another major chord. Happy birthday to you. You know, that's it. If it's one of your birthdays, happy birthday, okay? All right. So anyway, you see, when you're playing a song like that, you want it to sound consonant. You don't want it to sound dissonant, but sometimes you do, just not if it's a happy song. So for example, happy birthday, if I just make it all minor, okay, if I add some dissonance to it, then it's going to sound like this. Happy birthday to you. Happy birthday to you. You know, happy birthday, happy birthday. Okay, it sounds like a funeral. Happy birthday to you. You know, like that. Sounds brutal. I should have said to you like that. Anyway, that's a very sad birthday. Okay. You get the idea. So what I did was I changed it from consonant to this. That's very happy. But then I just take that one of those notes, take the 5th harmonic and make it complex. And now all of a sudden it goes from sounding like this to sounding like this. And that changes the feeling, right? So that's what we mean by dissonance, that feeling of angst or sadness or whatever. And of course, sometimes you want a song like that. It just depends on what you want. So you understand, now you understand what a consonance is, what dissonance is, how you get consonance. You get consonance by keeping it simple. So in other words, by keeping your notes, your frequencies, so that they boil down to simple ratios between 1 to 5, 1 to 6, okay, in numbers. And they'll sound very simple, highly consonant, okay? Now, if you want dissonance, you make those ratios complex, and sometimes that's desirable too. Yes, I can't use the Xbox right now. I'm recording.
And are you going to be done soon?
In like 3-4 hours.
Seriously?
No, it won't be that long.
How long?
That's my son, kids. That's my son, Benjamin.
And how long?
I don't know, like 15 more minutes. Okay. Oh, the joys of recording at home. Okay, so yeah. All right, so consonance and dissonance, done. Now, here's the deal. There's one other thing I'd like to go over with you, this concept of octaves. Now, an octave is when you double a frequency. Okay, now there are 7 octaves on my piano. So the lowest note I can play is an A way down here. I'm not sure how well that comes through on your speaker, but an octave higher is another A. And then another A, another A, another A. All the A's. Okay, these are all A's. Now, what makes an octave an octave? Well, when you double the frequency, okay? So you have to double it, but you have to keep doubling it. So let me explain. Let's say the lowest A I can play is this one. I'll go a little bit higher. That's around 120 hertz, roughly speaking. I'm not getting these frequencies exactly right. It doesn't matter. You can look them up in a table. Whatever note, 120 hertz, let's say it's this, okay? An octave higher would be double that. So you go to 120 to 240. That's 1 octave. Now, by the way, half of that, so 120 divided by 2, you get 60. That would be a lower octave. Okay, so octave means you're doubling, okay? Or if you go an octave lower, you're halving the frequency, cutting it in half. Okay, so if I go from 120 to 240, sounds like that. But what if I want to go the next octave? Well, I'm not going to double 120. I already did that. I have to double the previous octave. So I go from 240 to 480. So 240 to 480 sounds like, so 120 is 1 octave. Okay, it's the first note, the tone, if you like. 1 octave higher, 2 octaves higher. And then double 480 is 960. That's 3 octaves higher. And I double it again, 1920. That is 4 octaves higher. Okay. Now they correspond to all the even harmonics that like are multiples of a power, that are a power of 2. Okay. So for example, I didn't mean to tap my screen there. Okay. So for example, the second harmonic, the 4th, the 8th, the 16th, these are all powers of 2, you'll notice. 2 is 2 to the power 1, 4 is 2 squared, 8 is 2 to the power 3, because you're always doubling, right? So octaves mean you are doubling. Oops, I'm gonna spell that right. D-O, saying it, just not writing it. D-O-U. You're doubling, okay, the frequency. And that's it, okay? And basically, that's all we're going to talk about for music. It's very straightforward. There's not much else to say. Okay, there are some questions in the homework where they give you some, you know what, I'm going to pull up the homework here now for you. Let's see if I can do that. Hopefully it won't give me too much trouble. Okay, so let me just call up some of your homework and I'll show you what I mean. Why don't I save you some trouble, guys? Okay, because I know how busy you are. So let me save you some trouble. And let's look at the homework. So I think the homework starts on page, for this particular one, on page 279. Okay, so page 279. All right, so let's go to page 279, and I hope you can see what we're doing. Page 279 in your textbook looks something like this. Okay, now number 1 and 2 on page 279. Okay, it says describe the difference between objective and subjective properties. So objective ones are like frequency, amplitude, wavelength, stuff like that. These are, sorry, not subjective, but objective. Okay, these are characteristics of the wave that can be measured independently of your psychology. Okay, now your experience of sound is subjective. So the pitch, okay, the loudness, the okay, pitch and loudness. What else was I going to say? Oh, consonance and dissonance. Okay, these are subjective terms, and you know the difference between them is objective ones can be measured independently, can be sort of independently quantified using some measuring device. Okay, and I just gave you some examples to sound and music. So pitch, all the subjective ones are the ones that we defined before. So for example, pitch, loudness, consonance, dissonance, and so on. Okay, and that's good enough. All right, now it says here, which traces in figure 1 are pure tones? Okay, so let's look at figure 1 here for a moment. If I can find it. I'm sorry, I have to zoom out. It's a little shaky. That's figure 2. Oh, figure 1. Okay, here we go. Okay, so which ones are pure tones? Well, in order for it to be a pure tone, it has to be only one frequency. Okay, so let me turn on the annotations here for a second. That one is a pure tone. Okay, why is it a pure tone? Well, there's only, it's just a stable frequency, right? Like in other words, it's a constant wavelength, and there's only one wavelength. There's not more than one kind of wave overlapping there. So that would be a pure tone. This one here is also a pure tone. So tuning forks produce waves like that. Okay, sound waves. This one here is more than one harmonic. So these two are pure. These are pure. This one here is, it would sound consonant, but it's more than one harmonic. So there are two harmonics here. Same thing here. There's two or three, maybe even there. I think there's three harmonics here. Okay. Now this is like, that's dissonant. There's now overlapping tones that are very close together in frequency, and they produce that really noisy kind of looking wave there. And that would be a dissonant one. All right, so now I've done that one for you. And let's clear that. Let's close this. Let's go back to the question. So we did figure 1. Okay, which ones are pure tones? Well, they just asked us which ones are pure tones. The highest dissonance would be the noisy one there. And the reason why it's like that is because the tones are highly complex. They're very close together in frequency and they don't reduce. And that's why the wave looks like that. Okay. It's a really fuzzy looking wave with many overlapping tones that are close together in frequency. All right, so that's it. Oh, so that takes care of this page. Now I wanted to go to a different homework question. So let's look at the next page. I think it's the very next page, to be honest with you. So let's take a look. Page 280. Yes, it is. Okay, so go page 280. Look, we're doing the homework together. Wonderful. Okay. Octaves. Now, isn't this wonderful? We just talked about this. Okay, so look, here's the deal. You have a sound that has a frequency. The tone is a frequency of 220 hertz. What is one octave higher than that? Well, you would double it. This would be 440. What about one octave lower? Well, you would cut it in half. So it'd be 110. And it's very simple. Octaves, easy. Okay. You can say you're welcome, Mr. Flynn, you know, because, or sorry, you can say thank you, Mr. Flynn. I'll say you're welcome. You can say thank you, Mr. Flynn, for including such an easy question on a test, right? So octaves, you just either double or half the frequency to get an octave, and that's it. Now, if you look at the next question, it says for each pair of notes listed, write them as a simple fraction and determine which pair has a higher consonance. All right, so 600 to 400 can be reduced, first of all, to 6 to 4, so we can divide both of them by 100, but then they're also divisible by 2. So this boils down to 3 to 2. Now that's on our list of 1 through 5, so that's pretty consonant. Now what about 800 to 700? Well, that boils down to, in lowest terms, 8 to 7. This is more complex. Okay, so therefore the higher consonants would go to the simpler one, 3 to 2. And you see how easy that is? That's really all there is to it. Okay, so with that in mind, pardon me, gosh, a little tired. Okay, there are some more questions here that we could cover, but they're basically all the same. There is one question that's later in the homework about vibrating strings. Okay, yeah, you don't have to worry about that one. Or this one, I think we skip ahead a few pages till we get to the next homework. Okay, so if you look at this, what does the quality of a note depend on? Quality depends, okay, quality in the term of consonance and dissonance, how simple the ratio of frequencies are, okay? So the simpler they are, the higher the quote quality of the sound. Okay, now for each pair of the sounds below, choose one that has the higher quality. So a high consonance would have a higher quality, high dissonance would have a lower quality. Frequency 9 to 8, okay, or pairs of sound frequency 3 to 2. Well, pardon my yawns, oof, past my bedtime. 8 o'clock, okay. Anyway, yeah, 9 to 8, that's in lowest terms already. 3 to 2 is also in lowest terms, but 3 to 2 is simpler, so it would sound higher quality because it's more consonant. Okay, you get it? So that's it. And by the way, that last one there, FO and 5FO, well, that boils down to 1 to 5. Okay, so 1 to 5 would sound consonant. Pardon me, because it meets our criteria. I bet you're yawning because I just yawned, because it's contagious. Yawning is contagious. Now, what about F to 2F? Well, that boils down to 1 to 2. That will be more consonant than 1 to 5. Okay, now there is a question number 3 about strings. Do it because it's good review, okay, because harmonics and strings, we haven't looked at it for a while. So you might as well just do it. We answered questions like that, okay, in the past, so you should be able to do it, and I'll include it in the homework. All right, well, that's it for today's lesson. And by the way, if you have time, okay, on Tuesday, which will be the next time I see you, on Tuesday, we'll be doing review. And I did post a review test for you. So here's your review test. The test already has answers on it, but if you just want to print it without the answers, just double click on the PDF up here at the top, double click on that. It'll come up on your screen with no answers, print it, and then you can try answering it on your own. I did include a really sort of crappy formula sheet here. Don't worry about that. I have a better formula sheet for you that I will post in the notes, okay, before, tomorrow or something, or maybe even tonight. But I have a better formula sheet for you. You'll see some of the same questions you saw on your test that we already wrote, okay? And here we have some new questions like harmonics and tubes, okay, on overtones and so on, okay, like frequency and pitch and so on with music, etc. Pardon me. And octave numbers and Mach numbers and decibel levels and all that kind of fun stuff. And look, a diagram of the ear, and you have to know the structure to be able to label it, okay? and also to be able to state its function. Okay, there are questions here on open tubes and a closed tube. There's a question here on sonar. Okay, there's a question on redshift, which is just an explanation question. There's a question about bats and dolphins. There's a question about consonance and dissonance. There is, yeah, something about sonic booms. There's a funny wave question, and then there's a Doppler effect question. So anyway, it's a nice review. I put answers and solutions in there for you. So if you want to, on the weekend, you got time to kill, and it's pandemic and you're just bored, why don't you take a look at it? Because it's really your job to practice it, and then on Monday or Tuesday, pardon me, if you have questions, then great. Okay, you can have questions because you've checked it out already. All right, I'm gonna end it there. So have a good night, and we will talk to you on Tuesday. Have a great weekend. Okay, long weekend. Enjoy it. Enjoy a little extra break. And we'll talk to you soon. Okay, bye-bye.